Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the delicate world of unsolved puzzles, those shimmering riddles that even the sharpest minds still struggle to explain. Think of it as a slow, starlit walk through a gallery of mysteries, some dazzling and bright, others so faint and quiet you can only feel their presence when you stop and listen long enough. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly enjoy these calm explorations of the unknown. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always a joy to see how far our quiet constellation of listeners stretches across the planet. Now, let the lights dim just a little. Feel the rhythm of your breath slow and settle. The night outside can wait. The stars aren't going anywhere. If your mind begins to drift, let it drift. We'll still be here, gently unfolding the story, one calm thought at a time. You might imagine that after centuries of watching, measuring and writing, scientists would have found neat answers to most of nature's questions. But the universe, it seems, enjoys its little secrets. Every time we think we've untangled its threads, it ties a new knot, a burst of light that shouldn't exist, a law of physics that bends just enough to whisper, "Not yet." In tonight's quiet tour, we'll wander among those unsolved marvels, a handful of puzzles that remind us that curiosity, not certainty, is what keeps science alive. We'll begin with something sudden and dazzling. Explosions so fast and so blue, they make even supernovae look sleepy. These events, called luminous fast blue optical transients, or simply LFBOTs, appear for just a few hours or days, then vanish without explanation. Imagine staring into the night sky and seeing a flash as bright as a billion suns, gone before you can even tell where it came from. The first one was found by accident. A telescope scanning for asteroids caught it instead. It was named the Cow, after the final letters in its catalogue code. The name may sound gentle, but the event was anything but. It was a cosmic detonation unlike anything ever recorded. The light rose 100 times faster than a normal supernova and faded just as quickly as if the universe had blinked. Astronomers searched for clues in its afterglow, in its colour, in the way its radiation shifted across the spectrum. But nothing fit. The energy was too high, the light too blue, the pattern too short-lived. Some called it the most unsymmetrical explosion ever seen. It didn't bloom like a sphere, it shot out like a lopsided fountain of starlight. So they waited. And soon, other flashes appeared. The koala, the camel, the Tasmanian devil, and finally the finch, each with its own strange rhythm. Like a series of cosmic camera flashes, each one burned, flared, and fell silent, leaving behind no trace of the star that made it. The universe, it seemed, had invented fireworks we couldn't explain. As we move through tonight's journey, we'll visit not only these wild flashes but also quieter mysteries. The invisible pressure that makes galaxies drift apart, the quantum riddles that suggest light itself might be aware of being watched, planets wandering through space without stars to guide them, and a radio signal that beats once every 22 minutes, steady as a heartbeat, from a star that should have died long ago. Each story will unfold like a calm ripple in a pond, and together they form something deeper, a portrait of how much we still don't know, and how beautiful that unknowing can be. Science often feels like an endless conversation between light and darkness. Each discovery shines a new lamp, but the shadows grow longer just beyond its reach. For every question we answer, 10 more wait quietly in the dark, patient as stars before dawn. And that's the strange comfort of it all. The mystery is never gone, it only changes shape. You and I are living in a time when telescopes can see galaxies forming billions of years ago. when we can measure the faintest heartbeat of a distant planet, and yet, the more precisely we measure, the more the edges blur. It's as if the universe is saying, you're getting warmer, but you're not quite there. In the coming hours, we'll move slowly, softly, from the explosive to the invisible, from what we can see to what we can only imagine. There will be moments when the story feels almost impossible, numbers so vast or so small that they slip right through the fingers of understanding. When that happens, don't worry about the math. Instead, picture the feeling. When we say that the energy of empty space should have been 100 trillion times greater than it is, imagine it as a cosmic dial tuned so precisely that a tiny nudge either way would have erased the chance for life. When we talk about photons existing in two places at once, picture a single raindrop splitting to fall on both sides of an umbrella at the same time. When we mention a planet drifting without a sun, think of two travellers holding hands in an endless night. These images aren't replacements for science. They're ways of listening to it with the heart as much as the mind. By the time we reach the end of this quiet voyage, there won't be final answers waiting, but something gentler, the sense that wonder itself is enough. We'll find that the mysteries which frustrate scientists are also the ones that make our world feel alive. The universe is not a solved puzzle, it's a story still being written. And for those who stay up to read it, late into the quiet hours of the night, that's the most soothing thing of all. So let's begin where every mystery begins, with a single flash of light, too brief to grasp, yet bright enough to change how we see the dark. It began as many discoveries do, not with a plan, but with an accident. In June of 2018, a telescope in Hawaii called the Asteroid Terrestrial Impact Last Alert System, or ATLAS for short, was performing its nightly scan of the sky. Its purpose was simple: to look for asteroids that might one day wander too close to Earth. But that night, something else wandered into view. In a small region of the Hercules constellation, the telescope caught a sudden, dazzling flash. It was a burst of light 100 times brighter than a typical supernova, and then, within days, it faded back into darkness. The event was officially named AT 2018 Cow, but astronomers quickly took to calling it simply the Cow. The name might sound almost comical, but to those who study the death of stars, this event was unsettling, even haunting. The Cow did not behave like anything they had seen before. Most supernovae take weeks to reach their peak brightness and months to fade. The Cow, on the other hand, erupted to full brilliance in less than 3 days, then dimmed just as fast as if the cosmos had flicked on a light switch and then turned it off again. In that brief moment, it released more energy than the sun will produce in its entire lifetime. When astronomers examined its light in detail, they found even stranger things. Instead of the smooth curve of brightness typical of a dying star, the Cow's spectrum showed jagged peaks and sudden dips, as though something inside it were pulsing and breaking apart. Its light was unusually blue, meaning it came from extremely hot material, and it shone not just in visible light but in X-rays, ultraviolet and radio waves. It was, in every sense, a cosmic multi-instrument symphony played at once. But the melody made no sense. The initial guess was that the Cow was a supernova, the explosive death of a massive star collapsing under its own gravity. That explanation worked only for a moment. When astronomers looked closer, they noticed that the Cow's explosion wasn't spherical, as most supernovae are. Instead, it appeared wildly uneven, like a blast escaping through one side of a cracked shell. Some scientists described it as the most distorted stellar explosion ever recorded. The usual supernova models couldn't explain it. So, the theories began to multiply. Some suggested that the Cow might have been a massive star collapsing directly into a black hole, leaving behind a newborn monster that devoured the surrounding gas and dust. Others thought it might be a neutron star, the dense, spinning core left behind after a supernova, that somehow survived the blast and began emitting powerful jets of radiation. And still others proposed something stranger, that perhaps the cow was the birth cry of a black hole swallowing a nearby star. Each idea seemed possible, but none fit perfectly. Astronomers tried to make sense of it by comparing it to other known events, and then, as if on cue, more blue flashes began to appear across the sky. Later that same year came the koala and the camel, and 2 years after that, the Tasmanian devil. Each one shone for only a few days, each one burned hot and blue, and each one defied every model. With every new sighting, the mystery grew deeper. To an astronomer, this kind of repetition is both thrilling and maddening. One event can be dismissed as a fluke, 2 can be coincidence, but 3 or more, that means a pattern, and patterns are what science lives for. The trouble was, even as the sample size grew, the puzzle only became stranger. Most of these explosions appeared near the spiral arms of galaxies, where massive stars are born and die, suggesting they might be an exotic kind of supernova after all. But then came the Finch, the one that broke the rule. Discovered in 2023, the Finch erupted in the empty space between galaxies, about 3 billion light-years away from us. It had all the signatures of an elf bot, that same quick blue flash, that same staggering brightness. But it was floating in the dark, far from any place where stars should exist. It was like hearing a thunderclap in the middle of a desert where no clouds could form. For scientists, it was both exhilarating and deeply unsettling. If these events were caused by dying stars, how could one explode where no stars were supposed to be? 2 main explanations emerged. The first proposed that the Finch might be a star torn apart by an intermediate mass black hole. A kind of black hole that's heavier than those formed by collapsing stars, but lighter than the supermassive ones that anchor galaxies. Astronomers had long suspected that such black holes might exist in the quiet halos surrounding galaxies, possibly inside ancient star clusters, but they had never been proven. The Finch, with its violent outburst in the middle of nowhere, might finally be the clue they needed. The second theory involved a collision between 2 neutron stars, dense stellar remnants locked in a fatal orbit until gravity forced them together in a flash of light and gravitational waves. The problem was that when the Finch appeared, our main gravitational wave observatory, LIGO, was down for maintenance. No one could listen for the faint ripples in space-time that would have confirmed the event. It was like watching a fireworks show in silence with the sound switched off. And so, the truth remains uncertain. Astronomers are now turning to the new generation of telescopes, the James Webb Space Telescope, with its deep infrared eyes, and the Vera C. Rubin Observatory still under construction in Chile, to search for more of these blue flashes. They hope to find enough examples to build a proper story, to understand what kind of star or black hole or cosmic accident could produce such a brief but blinding flare. Until then, all they can do is wait and watch. There's something almost human in that. The patience, the persistence, the acceptance that not all mysteries can be solved quickly. The night sky doesn't yield its secrets to those who demand them. It reveals them slowly, like a conversation that spans lifetimes. The astronomers who study elfbots know this well. Every evening they set their telescopes to scan, not knowing if they'll catch another flash, another fleeting heartbeat of light from across the universe. Some nights, the sky remains silent. Other nights, it blinks, just once, and leaves them with more questions than before. Maybe that's the quiet lesson hidden in these cosmic camera flashes. The universe doesn't just show us its beauty, it teaches us patience. It reminds us that not everything bright lasts long, and that sometimes the briefest events can illuminate the biggest truths. The cow and its kin are not just explosions in the dark, they are reminders that even in the most fleeting moments there's meaning. The cosmos is speaking. We just have to learn how to listen in flashes, not in words. Imagine standing beneath a vast black sky, the kind of silence where even your own breath feels loud, and seeing, for just a heartbeat, a flash so intense that it lights up the heavens. That's what astronomers experienced when they found what they later named the Finch. It wasn't the first of its kind, but it was the one that broke all the rules. For years, researchers had been trying to understand these mysterious blue flashes, the LF bots. They'd built theories, drawn neat diagrams, and convinced themselves they were closing in on an answer. Then the Finch arrived, and every neat answer came undone. Up to that point, every one of these brief explosions had been found inside a galaxy's spiral arms, the bright star-forming neighbourhoods where massive stars live fast and die young. That made sense. Massive stars end their lives in supernovae, and even strange ones should still happen close to home. But when the Finch appeared, it was 3 billion light-years away, floating between galaxies, an expanse of emptiness where stars don't live, don't die, and certainly don't explode. It was as if a lighthouse had appeared in the middle of the ocean, shining with no coast in sight. Astronomers were stunned. Some even double-checked to make sure the coordinates weren't wrong. But the data was clear. The Finch was real, and it was glowing fiercely where it shouldn't. The only logical reaction was to start over, to let go of old theories and look again, as if the universe had said, "Nice try, but not quite." The first new explanation came from an idea that has haunted astronomy for decades: the existence of intermediate mass black holes. We know of black holes that are small, formed when a star collapses, and those that are immense, sitting at the hearts of galaxies. But this middle generation, those weighing perhaps a few hundred or a few thousand times the mass of our Sun, has always been suspiciously missing. They're too heavy to come from ordinary stars, too light to anchor galaxies, and too elusive for our telescopes to spot directly. Some scientists have long suspected these middleweight black holes hide in the faint halo surrounding galaxies, inside ancient star clusters that orbit the galactic edge. If that's true, then perhaps the Finch was a star that strayed too close to one of them, a cosmic bird caught in the gravity of a silent predator. Picture it, a sun-sized star pulled into a tight looping orbit around an invisible mass, each pass stripping away more of its body until it's shredded completely. The scattered matter would spiral in, glowing hot and blue before fading into darkness. The Finch's short, brilliant life could be the dying shimmer of that process, a kind of gravitational lightning strike. Simulations have shown that if such a black hole existed, it could tear a star apart over several orbits, each pass creating a flash brighter than the one before until nothing remained. It's a chilling idea, but also an elegant one. The problem is that we've never truly proven these intermediate black holes exist. We've seen hints, maybe footprints, but never the creature itself. The Finch might be the first whisper of one, or it might be something stranger still. The second theory turned to a different kind of cosmic violence: the collision of two neutron stars. These are the dense cores left behind when massive stars explode, so heavy that a spoonful of their material would outweigh an entire mountain. When two of them orbit each other, they slowly spiral inward, losing energy in the form of gravitational waves, faint ripples that travel through space like the echo of an earthquake through the fabric of reality itself. When they finally collide, they create a burst of light, heavy elements like gold and platinum, and a signature chirp in space-time. If the Finch was such a merger, it could explain the enormous energy and brightness. But nature can be cruelly inconvenient. When the Finch went off, our main gravitational wave detectors were silent. The LIGO Observatory, the instrument designed to listen for those cosmic ripples, was down for maintenance, so if there was a chirp, we missed it. No sound, no confirmation. It was like seeing lightning without hearing thunder, leaving us to guess what caused the flash. Even so, astronomers searched the data for anything else: gamma rays, X-rays, radio bursts, but the sky remained quiet. It was frustrating in the way only science can be, so close to revelation, yet still on the wrong side of certainty. One researcher compared it to standing outside a locked library, knowing the answers were inside but unable to open the door. For now, all that's left is patient observation. Scientists have turned their eyes back toward that lonely patch of sky, waiting for new instruments to help. The James Webb Space Telescope, with its deep infrared vision, might one day see the faint remnants of a globular cluster near where the Finch shone, the telltale home of an intermediate black hole. And when the Vera Rubin Observatory begins its sweeping nightly surveys of the southern skies, it could find more of these fast blue transients, adding new pieces to the puzzle. Science often moves forward in these strange half-steps, an explosion here, a mystery there, each one forcing the story to be rewritten. What's most striking is how gracefully the universe refuses to be predictable. It doesn't care about our equations or our comfort with neat explanations. It's full of quiet rebellion, flashes in forbidden places, light that shouldn't exist but does anyway. And maybe that's what makes discoveries like the Finch so haunting. They remind us that knowledge is not a straight path. It's a spiral. Every time we loop around, we see the same mystery from a new angle. One day, we may understand why these blue flares exist, what mechanism drives them, and how often they occur. But until then, the astronomers who chase them will keep watching. They'll point their telescopes toward the dark, scanning the edges of galaxies and the voids between them, hoping to catch one more flash. There's something beautifully human about that. The willingness to search without promise, to look into silence and expect to find meaning there. The Finch's light has long faded, its brief message already billions of years old when it reached us. But in that message was a kind of poetry, a whisper that even the loneliest corners of space have stories to tell. Perhaps in some forgotten corner of the cosmos, another flash has already begun, waiting for our eyes, our patience, and our quiet wonder to find it. When you look up at the stars, it's easy to think of space as a kind of quiet emptiness, a vast sea of nothing where galaxies float like drifting islands. But the truth is far stranger. Even the emptiest space you can imagine is not truly empty. It hums with invisible energy, a pressure so faint you would never notice it, yet so persistent that it drives the entire universe apart. This mysterious pressure is what scientists call dark energy, and the strange thing is, it should have destroyed everything. The story of dark energy began not with discovery, but with surprise. In the 1990s, astronomers studying distant supernovae noticed that galaxies weren't slowing down as they moved away from one another, as gravity would predict. Instead, they were speeding up, as though the universe itself was stretching faster and faster over time. That acceleration meant that something, some hidden force, was pushing against gravity. Einstein, decades earlier, had added a small term to his equations called the cosmological constant, a kind of gentle counterweight to gravity to keep the universe from collapsing. He later called it his biggest mistake. Yet here it was, reappearing in the data, as if the cosmos had decided to use Einstein's abandoned idea after all. In simple terms, dark energy is the name we give to that invisible push, the gentle anti-gravity woven into the very fabric of space. It doesn't pull or push through normal forces the way wind or magnetism does. It's more like space itself is breathing, every stretch of emptiness creating just a little more of itself. And while that growth is almost unimaginably slow on human scales, over billions of years it becomes powerful enough to scatter galaxies apart. The real mystery lies in how perfectly tuned this energy seems to be. To exist as it does, dark energy must have an incredibly small value. So small that if we tried to describe it with ordinary numbers, we'd have to say it's around a billionth of a joule in every cubic meter of space. That's less energy than the warmth carried by a single candle flame spread across an entire house. But when scientists tried to calculate what quantum physics predicts that energy should be, the answer came out catastrophically wrong. The theoretical prediction was not just a little higher, it was astronomically higher, larger by a factor so huge it defies language. Some call it the most inaccurate prediction in the history of science. To make that scale imaginable, picture this. If you stacked every grain of sand on Earth, you'd have around 10 to the power of 20 grains, a 1 followed by 20 zeros. The mismatch between theory and observation for dark energy is roughly 10 to the power of 120. It's not just off by a lot, it's off by a number so absurd that no analogy really fits. It's as if the universe balanced its own cosmic equation to a precision finer than 1 part in a trillion, an impossibly delicate harmony that made the difference between existence and nothing at all. And yet, here we are. The numbers, however unbelievable, work out in a way that allows stars to form, galaxies to take shape, and planets to orbit in calm, steady patterns. If dark energy had been just a little stronger, space would have expanded too quickly for atoms to gather, and the universe would have ended as a thin mist of radiation. If it had been even slightly weaker, gravity would have won, pulling everything back together into a cosmic collapse. Either way, no light, no warmth, no us. Somehow, the universe found the narrow middle ground. It's tempting to think of that balance as coincidence, a cosmic accident so lucky that it borders on impossible. But many physicists feel uneasy with that explanation. They don't like luck when the odds are too high. If we simply happen to exist in the one universe that hit the jackpot, it would be like rolling dice 100 trillion times and watching them land perfectly every single time. So, scientists began to wonder, is there something deeper we're missing? Some theories suggest that maybe the vacuum energy predicted by quantum physics isn't wrong, just incomplete, that there could be hidden forces or particles that cancel out most of the expected energy, leaving only the tiny remainder that we observe. Others take the idea even further and suggest that we might live in just one universe among countless others, each with its own physical laws. In such a scenario, it's not that our universe is special, it's simply one of the few where the numbers happen to allow for life. All the others, too dense or too empty, would pass by unnoticed because there would be no one there to see them. Still, this fine-tuning leaves many uneasy. It feels too perfect, too delicate. A few scientists, half in jest, call it the Goldilocks problem. Not too much, not too little, just right. When you look at the cosmic scales involved, the improbability feels almost poetic. The universe has existed for around 14 billion years, spread across a web of galaxies 2 trillion strong. Yet all of it depends on the faintest pressure imaginable, woven into the emptiness like a quiet note in an endless song. If that number, that whisper of energy per cubic meter, had been even slightly different, the symphony would never have begun. There would be no stars to sing, no elements to form, no consciousness to wonder. It's almost enough to make you pause and breathe more slowly, aware that existence itself might rest on the softest of balances. Perhaps that's what makes the study of dark energy feel less like pure physics and more like philosophy in disguise. It reminds us that the universe isn't just a set of equations, it's a story that depends on its rhythm being just right. Somewhere between expansion and collapse, between too much and too little, it found a space where beauty could exist. And perhaps that's all the explanation we'll ever need. That we live in a universe whose perfection lies not in understanding, but in the fact that it allows us to look up, to wonder, and to keep asking why. There's a quiet saying among cosmologists that the universe seems suspiciously well behaved. The forces that govern it are balanced so precisely that even the smallest change would have rewritten everything. Tonight, let's linger with that thought for a while, because behind the equations and observations lies something almost emotional, a sense of wonder that things turned out just right. In the late 1980s, a physicist named Steven Weinberg began asking a strange question. If dark energy really existed, this faint pressure that stretches the fabric of space, how strong could it be before it made the universe uninhabitable? He ran the numbers, filling page after page with estimates. What he found was astonishingly simple and impossibly delicate. If the energy of empty space were more than about 1/100th of a millionth of a joule per cubic meter, a number so tiny it barely seems real, galaxies would never have formed. The expansion of space would have torn matter apart before it had a chance to clump into stars. And yet, when astronomers later measured the actual value, it turned out to be almost exactly that, just a few times smaller, within the narrow window that allows light, gravity, and chemistry to exist. Think about that for a moment. If the universe had been a musician tuning a string, it would have needed to tighten it by exactly the right fraction of a turn, not too slack, not too taut, to let the melody of creation play. Anything else, and there would have been silence. Weinberg's realization gave rise to a curious idea, the anthropic principle. It sounds philosophical, but it's really just a statement of perspective. The reason we observe a universe suitable for life is because only such a universe could ever contain observers in the first place. If there are countless other universes, each with different settings for their cosmic dials, different strengths for gravity, different amounts of dark energy, then it's not surprising that we find ourselves in the one where life is possible. We couldn't have existed anywhere else. It's like being surprised that you happen to live on a planet with breathable air, forgetting that you couldn't have lived on one without it. This idea makes some scientists uneasy. It sounds to them like giving up, like shrugging and saying, "We're just lucky." Physics has always chased deeper causes, searching for mechanisms, not coincidences. Yet the anthropic idea doesn't end the conversation. It changes it. It asks us to think bigger, to imagine a universe, or perhaps an infinite number of them, where all possibilities are played out somewhere. In some of those, gravity might be stronger, stars burn faster, and time itself could unfold in rhythms we can't imagine. In others, matter might never form at all. We just happen to exist in the quiet corner where everything works. There's a strange comfort in that thought. It replaces arrogance with gratitude. The fact that the cosmic numbers came out right is not proof of destiny, but an invitation to awe. You don't have to believe in design to feel humbled by how narrow the path to existence truly is. When cosmologists run their simulations, adjusting parameters like the strength of dark energy or the density of matter, they find that most universes either collapse too quickly or expand too fast for anything interesting to happen. Out of billions of theoretical variations, only a few produce galaxies, stars, and life. And somehow, one of those few is ours. Maybe the better way to think of it isn't luck, but harmony. Imagine an orchestra tuning before a performance. Each instrument plays its note, slightly discordant at first, until slowly they align into a single chord. That chord is our universe, a fleeting balance between forces that might never repeat the same way again. We are listening to a performance that began nearly 14 billion years ago, and we happen to be alive during one of its most melodic moments. For some scientists, that harmony suggests something profound about the nature of reality itself. Perhaps what we call the laws of physics are not fixed at all, but emergent, temporary agreements the universe made with itself. Just as ice, water, and steam follow different rules depending on their state, maybe reality changes its laws under different cosmic conditions. If that's true, then the universe we know is just one form in an infinite dance of possibilities. Others take a different view, one less poetic but equally humbling, that there's simply no reason at all. The universe doesn't owe us explanations, only patterns to notice. Maybe we just drew the winning ticket. Maybe we exist in the same way that a raindrop forms on one leaf and not another, not because it was meant to, but because it could. Still, for every scientist who rejects the idea of cosmic coincidence, there's another who embraces the wonder of it. Even Weinberg, ever the pragmatist, admitted a certain unease. He once wrote, "The more the universe seems comprehensible, the more it also seems pointless. And yet in that tension between comprehension and meaning, there's a kind of quiet poetry. The very fact that we can ask these questions, that we can measure invisible energy and trace its effects across billions of light years, might be meaning enough. When astronomers point their instruments toward distant supernovae to measure the acceleration of the universe, they're really listening for balance. The faint whisper that holds everything together. They're searching for the same delicate tuning Weinberg calculated decades ago, the same near-perfect value that keeps galaxies from unravelling. And though they may cloak it in technical language, there's something deeply human beneath it all. A longing to understand why we exist in the rare space between too much and too little. If the cosmos truly is a multiverse, filled with endless variations, then perhaps wonder itself is universal too. Maybe somewhere, another species under another sky looks up and feels the same mix of gratitude and confusion. Maybe the feeling of being improbably alive is the most common emotion in creation. We don't yet know whether there are other universes, or if this one somehow chose its own rules. But we do know this. Every star we see, every planet, every heartbeat, every question you've ever asked, all exist because the fabric of space decided to expand at just the right rate. The odds were impossible, and yet, here we are, breathing in a universe that seems to have made room for us. Close your eyes for a moment and imagine the universe not as a single expanse of stars, but as a vast ocean filled with bubbles. Each bubble floats quietly beside countless others, and inside each one an entirely different version of reality unfolds, with its own stars, its own laws, its own meaning of what possible even means. That is one of the most daring ideas science has ever whispered, that our universe may not be alone. For as long as people have looked at the sky, we've tried to picture what lies beyond it. Ancient thinkers spoke of crystal spheres, invisible heavens, or mirrored worlds that moved just out of reach. But in modern physics, the notion of other universes is not mythology. It's a serious attempt to explain why this one behaves the way it does. It's a way of answering the question that dark energy raises. Why is the universe's expansion tuned so precisely for life? Why do the numbers fit so perfectly when they so easily could not? The idea of multiple universes is not one single theory, but a family of them, each with its own kind of infinity. Some versions are mathematical, some philosophical, and some sound almost like dreams told by space itself. But they share a common theme, that the cosmos might be far larger, far stranger, and far more varied than the tiny patch of reality we can see. The first dream is the cyclic universe, a vision where time itself breathes. In this picture, the universe is not a one-way journey from beginning to end, but a heartbeat that repeats endlessly. It expands, cools and fades until gravity slowly gathers it back together. Then, in one final pulse, everything collapses, only to burst outward again in a new big bang. Birth, death, rebirth, an infinite rhythm, like the tide coming in and out. Every star, every life, every moment you've ever known would be one wave among countless others. Some physicists find comfort in that idea. It means the cosmos never truly ends, it just changes form. Even if everything we know vanished, something new would follow, a universe remembering itself through cycles of creation. The second dream is the spatial multiverse, the idea that beyond the edge of what we can see, other regions of space stretch on forever. Our universe, the one filled with galaxies and dark energy and us, might be just one bubble in an infinite foam. In those distant realms, the laws of physics could be slightly different. Maybe gravity is weaker there, or light moves faster, or time flows in curves instead of straight lines. The distances between these universes would be so enormous that no signal could ever cross them, meaning we could never meet our cosmic neighbours. And yet, if inflation, that early burst of expansion after the Big Bang, is true, then such bubbles might be not only possible but inevitable. The universe may have blown itself into an endless field of pockets, each with its own version of reality. We simply live in one that happens to support the delicate chemistry of life. It's a humbling thought. Somewhere beyond our horizon, there could be universes where stars never formed, where matter never cooled, or where everything unfolded at such a dizzying pace that no atoms ever had time to come together. And yet, even knowing we can never reach them, something in us wants to imagine them anyway. There's a gentle defiance in that, the same kind that led our ancestors to sail beyond sight of land, trusting there might be more beyond the mist. The third dream is perhaps the strangest, and also the one closest to home. The quantum multiverse, born from the curious behaviour of particles themselves. In quantum physics, everything that can happen does happen, but not all in the same timeline. Each event, each decision, each tiny quantum choice causes reality to branch, splitting into countless versions that coexist invisibly beside one another. When a particle takes one path, another version of it takes a different path, and both outcomes remain real, separated by the thinnest veil imaginable. If you follow that logic far enough, then every moment in your life, every choice you made, every chance you took or didn't take, might exist in its own parallel thread of reality. Somewhere, another version of you chose a different path, said a different word, or stayed a little longer in a moment that passed too quickly here. And somewhere else again, an entirely different universe exists, governed by different constants, where maybe even the idea of you has no meaning at all. It sounds poetic, even romantic, but it's grounded in the same equations that describe how light moves, how atoms bond, how computers and lasers work. Physicists don't all agree on what it means. Some treat the many worlds interpretation as a mathematical convenience, others see it as a literal truth. But either way, it offers an answer, or at least a possibility. Maybe our universe didn't need to be perfect. Maybe all universes exist, and we're simply inside the one that allows us to ask why. It's impossible to say whether any of these dreams are real. They remain beyond proof, at least for now. We can't send a signal across the cosmic horizon, and we can't rewind time to watch the next cycle begin. But the power of these ideas lies not in certainty, but in imagination. They invite us to see existence as something more fluid, more creative, more generous than we once thought. If the cyclic universe is true, then nothing ever truly ends. If the spatial multiverse is true, then we are surrounded by infinities, each humming its own version of the cosmic song. And if the quantum multiverse is true, then every possibility, every path, every breath is part of an unimaginably vast pattern, one that contains all outcomes and still finds beauty in every single one. When you think of it that way, the multiverse is less a theory and more a lullaby, a way for the universe to remind itself that it doesn't have to choose just one story. Somewhere out there, in another branch or another bubble or another cycle, the same stars might be rising over different skies, and even if we can never see them, perhaps it's enough to know that existence itself is wider than our eyes can reach. In the end, whether there is one universe or many doesn't change the feeling that connects us to it. That quiet, wordless awe when you look into the dark and feel it looking back. We might be just one small consciousness in one small cosmos, but in that awareness, we are vast. Light has always been one of nature's favourite tricksters. It travels so fast that we use it to measure the size of the universe, and yet it behaves with a kind of mischief that makes even the sharpest minds hesitate. Sometimes it moves like a wave, spreading out and rippling through space like circles on water. Other times, it acts like a stream of particles, tiny distinct packets called photons. It seems to know when it's being watched, and it changes its behaviour accordingly. It's no wonder that Albert Einstein once described light as both wave and particle, but never both at once. Even now, physicists smile a little when they talk about it, as if discussing a friend who never quite tells the whole truth. The story begins in the early 19th century with a man named Thomas Young, who decided to shine a beam of light through two narrow slits in a screen. On the wall behind, he expected to see two bright lines, one for each slit, but instead he found a pattern of many lines, alternating bright and dark, just like the ripples that appear when two sets of waves overlap in a pond. That was proof that light behaves like a wave. Each beam interfered with the other, crest meeting trough, building or cancelling itself out. It was elegant and beautiful, the universe's quiet signature written in light. More than 100 years later, scientists repeated the experiment, but with a twist. Instead of a constant beam, they sent single photons, individual particles of light, one at a time. Each photon had to pass through one slit or the other. Yet when enough of them accumulated on the detector, the same wave-like pattern appeared. It was as if each photon had somehow gone through both slits simultaneously, interfering with itself. That shouldn't be possible. Particles don't do that. So the researchers decided to measure which slit the photon went through. They placed detectors at the slits to watch the light as it passed. And suddenly, the pattern vanished. The photons stopped behaving like waves and started acting like simple particles, forming two bright spots instead of many. The act of observing them changed the outcome. When unobserved, light was a wave exploring every possibility. When watched, it settled on one path. That paradox still echoes through every physics classroom and every philosophical debate about reality. How can observation, something that seems so passive, change what actually happens? It's as if nature only makes up its mind when someone is paying attention. Some scientists describe this in mathematical terms, with probabilities and functions that collapse when measured. But for most of us, it's easier to think of it as a cosmic version of a shy performer. When no one's looking, it dances freely across the stage. When the spotlight hits, it chooses a single pose and freezes there. Einstein struggled with this idea his whole life. He famously said, "I like to think the moon is there even when I'm not looking at it." He couldn't accept that reality might depend on whether someone is observing it. Yet every experiment since then has confirmed the same pattern. At the smallest scales, the universe behaves like a story that waits to be read before deciding how it should end. The more we learn, the stranger it gets. Light isn't just a messenger between stars, it's also the boundary between what we can know and what remains hidden. In a sense, it's the language the universe uses to tell us both everything and nothing at once. And within that paradox lies something oddly honest. Light doesn't pretend to follow our expectations. It shows us, over and over, that reality is not a fixed thing. It's a relationship, a dialogue between what is and what's being perceived. When we measure light's energy, we find that it comes in small discrete chunks, quanta, each one carrying just enough to move an electron or warm a surface. That idea, simple but revolutionary, was the birth of quantum theory. It told us that the universe isn't smooth and continuous but grainy, made of tiny indivisible steps. And yet, those tiny quanta still manage to flow together into the smooth daylight we see every morning. You never feel the jumps or gaps. The world feels whole, even though it is built from countless flickers. The deeper scientists dive into the nature of light, the more it blurs the line between the physical and the philosophical. If light can be in two places at once until we observe it, what does that say about time, or about cause and effect? If reality waits for an audience, who or what counts as the observer? Is it us, our instruments, or something more abstract? The universe noticing itself? These are not questions science can answer easily. They sit somewhere between physics and poetry. And yet they matter. Because light is not just a tool for seeing, it's a metaphor for knowing. Every time a photon reaches your eye, you're receiving information from the past. The light from your lamp left the bulb a fraction of a second ago. The light from the moon departed about 1 1/3 seconds ago. The light from the nearest star took more than 4 years to arrive. The light from distant galaxies began its journey billions of years ago, when the universe was young. To see is to look, backward through time, through all the choices reality has already made. And yet, when you gaze at the stars, the photons striking your eyes become part of your story too. They've travelled for ages just to end their journey here, in the quiet space of your perception. You collapse their possibilities into a single moment of awareness, a soft partnership between your mind and the cosmos. In that way, observation isn't just a disturbance to reality, it's the completion of it. The universe creates, we witness, and somewhere between the two, existence becomes real. So the next time you switch on a light, or watch sunlight glitter across a glass of water, remember, you're looking at one of nature's oldest riddles, a truth that refuses to sit still. Light is both wave and particle, both infinite and quantized, both mystery and messenger. It doesn't lie to us, it simply tells us that reality is larger, softer, and far more playful than we can imagine. If light could talk, it might sigh at how often we try to trap it, to make it behave. We build prisms, filters, and mirrors, trying to slice it into neat parts to see what it's really made of. And yet, every time we think we've cornered it, light finds a way to remind us that understanding is not the same as control. One of the most enchanting examples of this came from a deceptively simple experiment. One that used nothing more exotic than a few sheets of dark glass. Imagine holding up a pair of sunglasses on a bright day. Those lenses aren't just tinted, they're polarized, which means they allow light waves vibrating in only one direction to pass through. Light waves, unlike sound or ripples on water, don't just move forward, they also oscillate, vibrating side to side or up and down as they travel. A polarizing lens acts like a tiny gatekeeper, letting through waves that match its orientation while blocking those at other angles. If you take 2 pairs of polarized lenses and align them in the same direction, light passes through almost normally. But if you twist one lens 90 degrees, crossing the lines of vibration, the light disappears entirely. It's as if 2 invisible fences cancel each other out. Now comes the twist. The part that has puzzled students and delighted physicists for generations. If you take those 2 crossed lenses, which together block all light, and then slide a third polarizer between them at a diagonal angle, the light suddenly reappears. Not fully, but enough to see it shining faintly through, like a ghost. It's the kind of result that makes you smile and frown at the same time. Add another obstacle, and somehow the light finds a path again. On the surface, it seems like a contradiction. If each filter only allows light aligned with it to pass, then adding a third should make things worse, not better. But the quantum world loves to break our common sense in the gentlest way. What actually happens is that the diagonal filter changes the orientation of the light waves. When the first 2 filters were perfectly crossed, they blocked everything because their directions were incompatible, like 2 gates facing opposite ways. But the middle filter, angled halfway between them, acts as a translator, gently rotating the light's orientation so that part of it can slip through. It's not magic, it's geometry and probability dancing together. Still, that explanation feels too tidy for what the mind experiences when you see it happen. There's something beautifully poetic about it, that the act of adding something restrictive creates more freedom, not less. That sometimes introducing an obstacle doesn't dim the light, it helps it find a new way forward. The same logic, oddly enough, appears again and again in nature. You see it in rivers that flow around stones, in roots that twist toward light through cracks in rock, in the way sound can travel farther when echoed through narrow canyons. The universe seems to delight in finding harmony between opposites. In the world of quantum mechanics, this little game of polarization is more than a curiosity. It's a window into how light carries information and how particles make decisions. When physicists study the behavior of single photons, those tiny indivisible packets of light, they find that even an individual one can decide whether to pass or not, as if it's sampling possibilities before committing to one. In large numbers, those probabilities form the patterns we can see. But on the smaller scale, it feels like the photon is whispering, "I'll take this route, for now." Some experiments have taken this idea further, sending single photons through sequences of filters and measuring the odds of them surviving each stage. The results are always the same. Probability flows like a kind of invisible current, splitting and recombining depending on the paths available. You can't predict exactly which photon will make it through, but you can know how the group will behave. It's as if nature herself has built randomness into her routine, not as chaos, but as balance. If you stand back from the science for a moment, there's something deeply human about this paradox. How often in our own lives do we find that the things we thought would block us, a limitation, a change, a new rule, end up creating a path we couldn't see before? Light teaches this lesson effortlessly. More filters don't always mean less possibility. Sometimes, the very act of resistance reshapes what can pass through. There's another layer to this, one that stretches from sunglasses and laboratory filters to the stars themselves. Light travelling through space can become polarised by magnetic fields or cosmic dust, twisted as it journeys across millions of years. When astronomers study that polarisation, they can learn about the structure of galaxies and the invisible fields that shape them. The same principle that makes your sunglasses work also lets us trace the fingerprints of creation itself. It's humbling, really, that something as delicate as the tilt of a wave can tell stories about the birth of stars. It reminds us that complexity doesn't always live in grand gestures. Sometimes it hides in angles and orientations, in the quiet turning of light as it adapts to what stands in its way. And if you think about it long enough, you might start to see yourself in that light, literally and metaphorically. Every challenge you face, every layer of interference changes the direction of your energy a little, until finally, something that once seemed impossible becomes visible again. In that sense, physics becomes philosophy, and a sheet of polarized glass becomes a small, glowing metaphor for persistence. Perhaps that's what makes this experiment such a favorite among teachers and dreamers alike. It shows that nature doesn't just obey logic, it plays with it. It bends the rules just enough to make us wonder if we've misunderstood what rules really mean. Light, in its quiet way, keeps inviting us to see not only what passes through, but what it had to become to do so. The paradox of the polarizers is not really about glass and light at all. It's about transformation, how something changes just enough to continue its journey. Somewhere in that faint, reappearing glow is the essence of science itself: curiosity, adaptation, and the willingness to be surprised by simplicity. If you close your eyes and imagine light not as a steady beam, but as a series of small, bright moments, you'll begin to see what scientists at Imperial College London tried to do. In the spring of 2023, they built an experiment that asked a question so simple, it sounded like poetry. Can light interfere with itself not only across space but across time? They called it the temporal double slit experiment. You may remember the ordinary double slit test, where light is passed through two narrow gaps, creating a pattern of bright and dark stripes on a screen. The bright stripes are places where the waves add together, the dark ones where they cancel. It's one of the most famous demonstrations in physics, proof that light behaves like a wave. But in this new version, the two slits weren't side by side, they were moments apart. Instead of opening two holes in space, researchers opened two windows in time. The setup was both elegant and strange. They used an ultra-fast laser, pulses so brief they made ordinary flashes look like eternity, to strike a thin layer of special glass. Each pulse changed the properties of the glass for only a few trillionths of a second, just long enough for another pulse of light to notice. In those fleeting instants, the glass acted like a gate, opening twice in rapid succession. The two openings weren't separated by distance but by time. By less than a trillionth of a second, it was as if the experimenters had carved two moments out of the same heartbeat. When they measured the light that emerged, they found the same kind of pattern that appears in the traditional double-slit test, bands of brightness and shadow. But this time, the interference wasn't in space, it was in frequency, in colour. The light seemed to argue with its own past and future, creating ripples not along a surface but across moments themselves. Its colour shifted rhythmically, trembling between red and blue, as if it were undecided about which moment to belong to. There's a quiet beauty in that. A photon, a single quantum of light, is so small it has no real size, and yet it managed to reach backward and forward in time to interfere with itself. It's like watching lightning travel both directions through a storm cloud, one branch striking forward, another retreating to where it began. The equations behind it are dense and full of terms that only specialists love, but the feeling of it is simple. Light, the thing that defines how we see time, seems to slip through time as easily as through air. For a long while, physicists believed that the laws of nature were symmetrical, that time could run forward or backward without changing anything essential. In practice, of course, we never see time reverse, but experiments like this make the border between past and future look less like a wall and more like a curtain. Maybe the arrow of time isn't drawn by physics itself, but by the way we experience it, by memory and decay, and the way our hearts keep moving in one direction. When you think of it that way, the temporal double-slit experiment sounds less like a puzzle and more like a reminder. The photon isn't choosing between yesterday and tomorrow, it's simply exploring all possibilities until something, a measurement, a decision, a moment of awareness, invites it to settle on one. To the universe, all of those options might be equally real. To us, it's only after we look that the story becomes fixed. In the lab, this behaviour shows up as a fine pattern in the light spectrum, little peaks and valleys, each representing where the wave added or cancelled itself out across the two time openings. The pattern is faint but unmistakable. It's as though the photon whispered to its earlier self, asking, "Should we meet in the middle?" And both versions of the answer appeared in colour. Of course, no one thinks the photon is actually conscious. The language of choices and whispers is just the easiest way to describe what the equations already say. But language matters. It gives these abstract events a human rhythm, something the mind can hold on to. It turns numbers into stories. And stories, after all, are how we make sense of what we can't yet explain. What's truly remarkable is what this tells us about the nature of observation. When we measure a system, we're not just taking a snapshot of something that exists independently. We're participating in its definition, choosing which version of the story gets told. Before measurement, light seems to explore all paths, not just through space, but through time itself. Once measured, the paths collapse into one narrative, the one we see. It's a little like asking a child to pick just one colour out of a crayon box after they've already drawn a rainbow. The act of choosing changes the art. When you step back from the mathematics, the experiment paints a strangely emotional picture. Imagine time not as a river flowing in one direction, but as a still lake. Light is not swept along by it, but glides across the surface, sending ripples outward. Each ripple touches both what we call the past and what we call the future. The patterns we see, the trembling colours, the shifting frequencies, are the interference of those ripples meeting. And maybe, in a quiet way, we do the same. Every thought, every memory, every dream about tomorrow sends its own ripple through time. We may not notice it, but the universe might be listening, blending our small disturbances into its grand, slow symphony. So perhaps the question is not whether light can interfere with itself across time, but whether time can bear witness to itself through light. The experiment at Imperial College was a whisper from the cosmos, reminding us that the boundaries we draw between moments, between causes and effects, between what was and what will be, are gentler than we think. Maybe light doesn't travel through time at all. Maybe time and light are partners, reflecting each other endlessly. When you switch on a lamp or watch the first blush of sunrise, you're not just seeing photons moving through space, you're watching the universe remember itself in colour. And as the researchers packed away their instruments and turned off their lasers, the data still glowed faintly on their screens, a shimmering record of a beam of light touching its own echo. Perhaps time itself isn't a river. Perhaps it's a lake, and light just ripples across it, softly, beautifully, forever. If the temporal double-slit experiment hinted that light can whisper to its own past, the next question feels almost inevitable. What if the future can whisper too? In the quiet world of quantum physics, where events unfold like possibilities rather than certainties, that's not as far-fetched as it sounds. There's an experiment that captures this delicate paradox perfectly, one that makes even time itself seem politely uncertain about which way it's supposed to run. It's called the delayed choice experiment. The idea traces back to John Archibald Wheeler, a physicist known for turning science into poetry and questions into riddles. He asked something simple but unsettling. What happens if we make our decision about how to measure a particle after it has already travelled through the experiment? Can our choice in the present influence how the particle behaved in the past? Imagine the setup as a kind of cosmic hallway. At one end you release a photon, a single particle of light. Halfway down the hall it faces a choice. It can take one path or another. At the far end there's a device that can either tell you which path it took, or, if configured differently, erase that information and let the photon interfere with itself, like a wave that explored both paths at once. Wheeler's question was, what happens if you decide which measurement to make after the photon has already passed the halfway point? Does the photon somehow know what you'll choose? In laboratory versions of this test, scientists send single photons through mirrors and beam splitters, instruments that can divide and recombine light, and then delay their final choice about how to measure them until the photon is already en route. The results, repeated countless times, are astonishingly consistent. When you choose to measure which path the photon took, you find a clear answer. It behaved like a particle, picking one route. But if you choose to let the paths recombine, even if you make that choice after the photon has crossed the critical point, you see the interference pattern that reveals wave behavior. Somehow, your present decision determines the photon's past identity. It's as if a coin flipped yesterday waits to see today whether you'll decide it should land as heads or tails. Not because the laws of nature are broken, but because at this level, yesterday and today are threads in the same woven fabric, and the tug on one ripples softly through the other. The photon's journey isn't like a traveller walking from one end of a road to the other. It's more like a song played all at once, with every note influencing the harmony. To our everyday minds, that feels impossible. We live in a world ruled by sequence, cause first, effect after. You light the match, then the candle burns. But in the quantum world, causality is not so rigid. Events seem to exist in a kind of dialogue, deciding their meaning only when all is said and done. The future doesn't rewrite the past in the way a novelist might revise a page. It completes the story, smoothing the sentences, making sense of what came before. When researchers talk about this, they often use the language of information. Before you measure, the universe holds many potential stories. Measurement doesn't create the story, but it chooses which one becomes visible. In the delayed choice experiment, that selection happens in a way that transcends simple order. The photon doesn't commit to being a wave or a particle until the very end, when the measurement context is decided. Only then does it reveal a consistent narrative. one that fits perfectly within the rules of quantum physics, yet feels deeply at odds with intuition. Some interpretations say that the photon doesn't actually change the past, that the past simply wasn't defined until the present forced it to be. The difference may sound subtle, but it's profound. It suggests that the universe doesn't keep a permanent record of every detail. Instead, it holds potential until something, a measurement, an interaction, maybe even consciousness, gives it form. Reality, in this sense, isn't fixed like a photograph. It's more like a Polaroid slowly developing, the image coming into focus only when enough light, attention, and time have mingled together. Wheeler once extended this idea to a cosmic scale. He imagined distant galaxies whose light has been travelling toward us for billions of years. What if, he asked, we set up our detectors in such a way that we could choose, right now, whether to observe that ancient light as a particle or as a wave? Would our present decision influence the behaviour of photons that began their journey before Earth even existed? The equations say yes, at least in a way that defies any neat separation between past and present. Our observation today could determine how that ancient light acted billions of years ago. It's hard not to feel small and yet strangely connected when you think of that. Somewhere in the depths of time, a photon left a distant quasar, crossed the cold dark between galaxies, and finally met your gaze. Whether it travelled one path or two, whether it arrived as a wave or a particle, depended not only on where it started but on what choice you made when it arrived. The universe, it seems, waits for the story to be told before deciding how it began. Of course, physicists are careful not to interpret this as proof of time travel or magic. The laws of nature remain consistent. It's our interpretation of them that grows deeper. In the quantum world, information is the thread that binds time together. The moment we measure, we're weaving that thread into the tapestry of existence, closing loops that were open, finishing thoughts the universe began long before we existed. It's comforting in a way to imagine causality not as a chain but as a circle, an ongoing conversation rather than a strict command. The future doesn't erase the past, it helps it make sense. Each moment we experience, each question we ask, sends a quiet ripple backward as well as forward, completing patterns we might never fully see. So when you look at the stars tonight, remember that some of the light reaching you left its source long before humanity learned to walk upright. And yet, in a subtle, almost imperceptible way, your act of looking helps define that light's long-ago journey. The universe might not know the ending before the story begins, but it seems to write both at once. Pen in one hand, paper in the other, past and future bound together in the same graceful line. Out in the quiet arms of the Orion Nebula, beneath swirls of gas that shimmer like ocean waves caught in starlight, the James Webb Space Telescope noticed something strange, a kind of dance playing out in the dark. What it saw wasn't the usual family of stars and planets, where a warm sun sits in the middle and planets glide obediently around it. No, these worlds had no star at all. They were pairs of planets, lonely, wandering giants, orbiting each other as they drifted through the void. Astronomers gave them a nickname that almost sounds affectionate: jumbos, short for Jupiter mass binary objects. About 40 of them were found in Orion, each about as heavy as Jupiter, moving together through emptiness like slow waltzes in a ballroom where the lights have gone out. If the cosmos ever had a sense of irony, this would be it. Because according to everything we know about how planets form, these couples shouldn't exist. Planets are supposed to be the leftovers from a star's birth, the dust and gas that doesn't quite make it into the star's body. They orbit because gravity binds them to the warmth that created them. Without a star, the story falls apart. How could two planets, both too small to ignite fusion, have found each other in the first place? And how could they still be together, holding on, when the universe's gravity tries endlessly to pull them apart? For scientists, this discovery was like hearing a duet with no orchestra, two voices keeping perfect rhythm in the dark. It doesn't fit any known theory. The usual rules say that once a star ejects a planet, flinging it away through a close encounter or a cosmic accident, that planet drifts alone forever, condemned to wander without a home. The odds of two such exiles meeting in deep space and locking into orbit are so low that they might as well be zero. Yet here they are, 40 pairs of worlds circling each other, calm and steady, as though they'd been there all along, waiting for us to finally notice. One possible explanation lies in the earliest chapters of star formation, in clouds of gas so thick and cold that light itself can barely pass through. Normally, gravity pulls such clouds together until a star ignites in their centre, but there's a limit to how small a fragment of gas can shrink and still collapse into a star or planet. Astronomers call it the opacity limit, a point where the gas becomes too dense for its own heat to escape. When that happens, the gas stops cooling and stops collapsing. It stays restless, half-born, unable to become anything more. Now imagine that instead of one big cloud forming a star, a small knot within it tears free, a clump of gas too light to burn as a star but too heavy to disperse. It might split in two before cooling, forming a pair of planetary-sized bodies. They wouldn't need a parent star at all. They'd simply drift off, bound only to each other, like cosmic twins left behind after the birth of a galaxy. That's one theory, that the jumbos were never planets in the traditional sense, but tiny failed stars that formed together and were set adrift. Another possibility is more dramatic, that they were once part of young star systems, thrown out during chaotic dances of gravity. When new stars are born, their surroundings can be crowded and violent. Massive worlds tug and pull at one another like dancers tripping over each other's steps. Sometimes one gets thrown out entirely. If two such exiles happen to be near each other at that moment, their mutual gravity might catch, binding them together before they slip away into the galactic night. It's a fragile bond, like two leaves caught in the same breeze, improbable, but not impossible. What makes this discovery so haunting is not just its rarity, but its tone. There's something deeply human about the image of two worlds holding each other's gravity as they drift through infinite space. Alone, they would be silent, cold, and forgotten. Together they create motion, a shared centre, a quiet partnership that turns isolation into rhythm. Astronomers studying these pairs often describe them with words you wouldn't expect in scientific papers: companionship, grace, even loneliness. Because in the end, it's hard not to project a little poetry onto such a sight. The data shows their masses, their orbits, their estimated temperatures. But the human heart reads it differently. We see a metaphor for connection, the idea that even in the coldest places something can still find something else to orbit. The Webb telescope's images of Orion reveal faint traces of light reflecting from these objects, their paths curving gently around invisible centres of mass. To translate that into everyday sense, if you could somehow stand on one of these planets and look at the other, you'd see a small, distant world hanging motionless against the starry backdrop, rising and setting not because of a sun, but because you and it are spinning around each other. Your day and night would be measured not by sunlight, but by the slow dance of your companion world. That's the kind of picture that lingers, a reminder that the universe allows for companionship even where we thought none could exist. The jumbos don't obey the familiar patterns of planet and star, master and satellite. They belong to a different kind of order, one born of chance, of imperfection, of the unpredictable generosity of gravity. In the years to come, scientists will look for more of them, hoping to find whether Orion's strange duet is unique, or just the beginning of a new cosmic category. If more pairs are found, it might mean that nature often finds loopholes in our laws, places where chaos breeds structure and accidents become systems, and if we never find another pair like them, then these 40 will remain a quiet miracle, a fleeting glimpse of something rare and complete. For now, we simply watch them from afar, two wanderers keeping each other company in the dark, moving to a rhythm older than words, older than life, older than even the stars themselves. Perhaps they are reminders that order is not always born from symmetry, and that beauty sometimes hides in the loopholes. The universe, it seems, never tires of finding new ways to say the same thing, that even in the coldest emptiness, connection endures. If the universe has a favourite habit, it might be the way it lets us make rules, and then gently breaks them. Astronomers spent decades believing that worlds couldn't form without a parent star. Then came those drifting pairs in Orion, defying every line written in the textbooks. When the first papers about them appeared, a few scientists smiled quietly, because more than 20 years earlier, someone had already suggested that magnetism might hold the missing key. His name was Alan Boss. Back in 2001, long before the James Webb Telescope existed, Boss had written about an idea that few took seriously at the time. He believed that magnetic fields, the invisible lines that thread through every cloud of gas and dust in space, might do more than guide charged particles. They could, he said, act as sculptors. Imagine a cloud so vast that it could one day form stars. Within that cloud, magnetic fields twist and tangle like unseen ropes, guiding how the gas moves. Boss suggested that in some places those ropes might pull too tightly. They could pinch off small knots of matter, flinging them away before the main star ever forms. Each knot, if dense enough, might become a planet-sized object, an exile born from magnetism itself. The idea was elegant, but it never caught on. At the time, no one had seen any proof that such lonely objects could exist, much less pairs of them. Science, like a careful gardener, often trims away its wildest branches. The paper was shelved, cited a few times, and then left to gather cosmic dust. And yet, here we are. 2 decades later, the Webb telescope catches glimpses of exactly what Boss described. Planet-sized pairs, far from any star, orbiting each other as if connected by an invisible thread. When news of the discovery spread, some younger astronomers searched through the archives and found his old prediction. One of them described it as a message from the past, waiting for the right eyes. Magnetic fields are among the most mysterious forces in astrophysics. We can't see them directly, but their fingerprints are everywhere. They twist the tails of comets, shape the birth of stars, and steer charged winds across entire galaxies. If they can also shape planets, it would mean that magnetism and gravity, the two great shapers of the cosmos, are more entwined than we ever imagined. Here's how scientists think it might work. Picture a cloud of interstellar gas, cold and enormous, hundreds of times wider than our solar system. Inside, magnetic fields thread through it like strands of silk, invisible but strong. When parts of the cloud start to collapse under gravity, the magnetic lines twist and pinch, transferring energy. Some regions spin up faster than others, flinging small clumps of matter outward, tiny seeds of what could become rogue planets. If two such clumps form close together, their mutual gravity can bind them before they drift too far apart. And just like that, a pair of worldlets is born, tethered by the same physics that gave them life. It's astonishing to think that something as intangible as magnetism could create something as solid as a planet. But this is how the cosmos often works. Invisible forces sculpt visible worlds. The very iron in our blood once followed magnetic paths through ancient stellar cores. The compass that points north on a sailor's ship is a quiet echo of the same field lines that spiral through the Milky Way. Every scale repeats a pattern of the same hidden geometry. When Alan Boss first described his magnetic model, he couldn't know that his theory would one day be rediscovered by a telescope orbiting 1 million miles from Earth. That's one of the gentle ironies of science. Ideas often drift in their own kind of orbit, forgotten for years until some new observation pulls them back into relevance. It's as if the universe holds onto every hypothesis, waiting for the right moment to nod in agreement. The discovery of the jumbo pairs gave that nod. The old theory returned, not as a triumph or a correction, but as a conversation resumed. It reminded the scientific community of something easy to forget, that knowledge doesn't move in a straight line. It spirals much like the galaxies themselves, revisiting places that once seemed familiar but now look different under new light. Today, new telescopes and observatories, like the Vera Rubin Observatory in Chile, the LISA mission in space, and the European Extremely Large Telescope, are being designed to study these free-floating worlds in greater detail. They'll search for heat signatures, for traces of magnetism, for faint gravitational wobbles that might reveal whether these planets have moons of their own. Each observation will add a few more notes to this quiet symphony of rediscovered ideas. It's easy, sometimes, to imagine science as a relentless forward march, each generation outpacing the last. But moments like this show how circular it really is. The universe doesn't care about our timelines, it cares about curiosity. An idea whispered in one century can find its answer in another. The pattern might take decades to unfold, but it always finds its way back. There's something deeply moving about that. A single scientist sitting alone in a quiet office once wrote that magnetic fields might throw small worlds into the dark. And now, telescopes the size of cathedrals orbit above us, confirming the shape of his dream. In that sense, discovery is not just about data, it's about patience. It's about trusting that the questions we ask today may bloom long after we're gone. Maybe that's the real lesson of the magnetic bridge. The forces that connect planets also connect generations of thought. Ideas, like worlds, find companions in the dark. They circle each other, exchange energy, and sometimes, when conditions are right, they shine again. And somewhere out there, in a quiet part of Orion, those twin planets continue their slow magnetic waltz. They don't know they've become symbols of persistence and rediscovery. They just orbit, silently fulfilling equations written in starlight, while we, far away, marvel at the elegance of rules broken and reborn. Every once in a while, the universe does something that feels personal, something so deliberate that it almost seems to have a heartbeat. In the southern skies of our planet, about 15,000 light-years away, there's a small region filled with the faint hiss of radio static. Most of that static is background noise, the cosmic hum left over from the birth of everything, but tucked inside it is one sound that repeats like a clock. It pulses every 22 minutes, not once a second as normal pulsars do, but once every 1300 seconds. Slow, steady and patient. Astronomers call it GPM J183910, though that name feels far too clinical for something so quietly poetic. To the people who discovered it, it's simply the beacon that refuses to die. When a star many times heavier than our Sun ends its life, it often collapses into a neutron star, a sphere barely 20 kilometers across but denser than any substance we can imagine. Inside, a teaspoonful of matter would weigh more than a mountain. These dead stars spin rapidly, some rotating hundreds of times each second, and they beam out radio waves from their magnetic poles. As they turn, those beams sweep across space like the light of a distant lighthouse, flashing each time one crosses our line of sight. That's what a pulsar is, a cosmic metronome born from destruction. But GPM J183910 isn't just another pulsar. Its pulse is impossibly slow. If you picture a normal pulsar as a drummer keeping frantic rhythm, this one is a single note stretched to the edge of silence. In theory, such an object shouldn't even shine. There's a region astronomers call the Death Valley of pulsars, a range where the magnetic and rotational energy should be too weak to produce any light at all. By all accounts, this star should have gone dark millions of years ago, yet it hasn't. For 35 years of careful observation, it has remained unwavering, sending its faint rhythmic message across the void. The first time scientists noticed it was back in the early 1990s, hidden within old data recorded by a radio telescope in Australia. It was only years later, when researchers revisited that data, that they saw the pattern emerging. Every 22 minutes a soft radio hum, then silence, then again, over and over for decades. To check that it wasn't an artifact, a glitch of the instrument, they looked through newer recordings. There it was again, always the same, as constant as a heartbeat in the dark. The puzzle left astronomers torn between fascination and disbelief. A typical pulsar loses its brightness as it slows down. The electric currents powering its beams fade away once its spin falls below a certain threshold. But GPM J183910 has crossed that threshold and kept going, glowing from a place in physics where nothing should glow. Two explanations have been floated. The first is that it might be an especially unusual magnetaire, a neutron star with a magnetic field trillions of times stronger than Earth's. That much magnetism can twist space itself, creating bursts of radiation and strange electrical storms. If this star's field were still decaying, it might keep releasing energy slowly, like an ember that refuses to cool. The second theory is that it could be an ultramagnetic white dwarf, the remnant of a smaller star that never became dense enough to form a neutron core. Such a white dwarf would be much larger, spinning slowly but generating enough field strength to produce radio flashes. Both models work on paper. Both also fail to explain the remarkable stability of the pulse. For 35 years, through every cycle of our own sun, the beacon has kept the same tempo. That constancy has a kind of quiet drama to it. We measure the spin of these objects by the precision of their pulses, and this one is so regular that some astronomers joke it would make a better clock than most devices on Earth. Imagine a lighthouse on a cliff, its lamp broken, yet the glow still sweeping the waves by memory alone. That's what this feels like, a star that doesn't realize it should be gone. When we translate the signal into sound, compressing the minutes into seconds, the rhythm becomes haunting, a slow thump, a pause, a faint echo. Some researchers play it through speakers when explaining the discovery, letting audiences hear the heartbeat of a dead star. It's not music in the human sense, but there's something undeniably emotional about it, as though the universe itself is keeping time. Each pulse we receive left the star 15,000 years ago, long before recorded history began. When it was emitted, the ice sheets were retreating from Europe, and early humans were carving stories into cave walls. Those signals travelled across interstellar space all that time, through dust clouds, through the magnetic fields of the Milky Way, through storms of charged particles, until finally they reached our instruments. We're listening to a message older than every civilization we've ever built. And yet the message is simple. I'm still here. That's all it says over and over every 22 minutes. It doesn't ask for attention. It doesn't fade. It just persists, a steady voice in a vast silence. When astronomers talk about this object, they do so with a kind of reverence. Not because they think it hides deep meaning, but because it reminds them how stubborn the universe can be. Physics loves rules, but nature loves exceptions. Somewhere out there, a star long past its prime still keeps perfect time, teaching us humility with every beat. If you listen closely, it's hard not to hear the metaphor. Everything that lives eventually slows down, cools, and fades. But even in that fading, there can be rhythm, something orderly, something faithful. The beacon may one day fall silent, its energy finally spent, but until then it keeps shining, defying both math and expectation. Perhaps that's why one scientist, when asked to describe it, simply said, "It's as if the cosmos left a light on, long after everyone went home." So, somewhere in the dark, a dead star keeps time for the living. Its pulse is older than our languages, steadier than our history. And as you sit here, listening to this story, another flash has already left it, racing invisibly through space, heading toward us. A message that won't arrive for another 15,000 years. For as long as humans have looked at the sky, we've tried to keep time by it. Ancient people marked the seasons by the sun's position, counted months by the moon's changing face, and measured their lives against the return of the stars. Even now, we still think of the universe as the ultimate clock, immense, impartial, and precise. But the deeper astronomers look, the more they find that the cosmos keeps several clocks at once, and none of them quite agree on what time it is. The slow, steady pulse of GPM J83910 is one such clock. Every 22 minutes, for 35 years and counting, it has sent its quiet message across the galaxy. To us, its rhythm feels absolute. And yet, when scientists turn their attention to the scale of the universe itself, to the expansion of space and the aging of galaxies, another kind of rhythm appears, one that refuses to match the first. If the pulse's beat is a heart, then the cosmos as a whole seems to breathe in a different tempo. For more than a decade, astronomers have been measuring how fast the universe expands. There are two main ways to do it, each elegant in its own way, and both should give the same answer, but they don't. One method looks at the nearby universe, the stars and galaxies close enough that we can measure their distances directly. These observations suggest that space is expanding quickly, adding roughly 73 kilometers of distance for every megaparsec, a cosmic unit equal to about 3 million light-years. The other method looks at the ancient universe, at the faint light left over from the Big Bang called the cosmic microwave background. That second clock says the expansion rate should be slower, around 67 kilometers per megaparsec. That 6-kilometer difference doesn't sound like much, but on a universal scale, it's enormous. It means that if both measurements are correct, something is missing from our understanding of how the universe grows. This disagreement is known as the Hubble tension, a term that sounds gentle but represents one of the biggest puzzles in modern cosmology. Astronomers have spent years checking and rechecking their data, recalibrating instruments, refining equations. Each side of the measurement seems sound. The nearby galaxies don't lie, and the ancient light doesn't either. It's as though the universe is playing two rhythms at once, one fast, one slow, and we're caught between them, unsure which to dance to. Some scientists suggest that dark energy might be changing over time, growing stronger as the universe ages. Others think there could be unknown particles influencing gravity on the larger scales, or that the geometry of space itself might be subtly curved in ways our current models don't capture. Whatever the reason, the universe is out of sync with itself. Its clocks are arguing. In a way, the 22-minute beacon and the expanding universe are mirrors of one another. One is too steady, a star that refuses to fade when it should. The other is too restless, a cosmos stretching faster than expected. Both defy the elegant order our equations promise, and both remind us that certainty in science is never permanent. It's something we rebuild constantly, pulse by pulse, measurement by measurement. It's tempting to see this tension as a flaw, as if the cosmos had made an error. But maybe it's not a mistake at all. Maybe the universe isn't a single clock ticking toward a conclusion. Maybe it's a symphony of rhythms, some fast, some slow, all overlapping and echoing through the dark. When physicists talk about time, they often describe it as a dimension, something we move through, like space. But time is slippery. It stretches and compresses depending on where you stand and how you move. A clock on a satellite, high above Earth, ticks slightly faster than one on the ground because gravity is weaker up there. When astronauts travel at high speeds, Time itself slows down for them relative to people back home. These aren't just ideas from thought experiments. They're measured effects confirmed again and again. Time, it turns out, isn't universal. It's personal. Each object, each observer, carries their own version of it. That makes the idea of disagreement almost comforting. Maybe the universe's mismatched rhythms are just part of its nature. Each galaxy, each star, each atom keeps its own kind of time. We notice the difference only because we're listening closely enough to hear it. Sometimes, late at night, when observatories sit in their quiet mountain air, astronomers describe the cosmos as an orchestra tuning itself. Each section adjusts, strings, winds, percussion, none yet in harmony. That's what discovery often sounds like, a long, slow adjustment, full of small dissonances that eventually lead to music. The Hubble tension may simply be part of that tuning, the universe gently correcting itself, asking us to listen a little longer before claiming to know the melody. If there's a lesson in all this, it might be the same one that the pulsar has been repeating for 35 years. The universe doesn't rush. It's patient, methodical, unbothered by contradiction. The beat will continue whether we understand it or not. Our job isn't to force the rhythms to match, but to learn how to hear them together. And so, the star that refuses to die and the cosmos that refuses to agree become parts of the same conversation. One local, one infinite. They both pulse with the same truth, that uncertainty isn't chaos, it's invitation. Every mismatch, every anomaly, is a doorway to a deeper understanding. Perhaps one day we'll discover why the universe's clocks disagree. Maybe new instruments, telescopes larger than cathedrals, arrays listening for the faintest tremors in space-time, will show us the missing notes. Or maybe we'll learn that the disagreement is the point, that reality was never meant to be a single rhythm, but a harmony of many. Until then, we measure, we listen, and we wait. The universe keeps its time in ways we can only glimpse, and every once in a while, it lets us tap our fingers along to its patient, uneven song. By now, we've walked through a strange garden of questions, blue flashes that fade before we can name them, invisible pressures that hold galaxies apart, photons that seem to wait for us to decide their fate, worlds that wander without suns, and a lonely beacon that beats beyond its death. Each mystery, on its own, feels like a puzzle still missing a few pieces, but when you step back and look at them together, they form something larger, a kind of tapestry woven from curiosity and confusion. It's not a perfect pattern, but it's beautiful precisely because of that. Science at its core is an act of listening. We often imagine it as a hunt for answers, but most of the time, it's a process of paying attention, of hearing whispers in the noise and realizing they mean something. The universe rarely shouts. It reveals itself through rhythm, color, and faint traces. And the more sensitive our instruments become, the more we notice that the cosmos speaks in many dialects, all of them poetic. Think of the Lephbots, those quick blue explosions like flashes of lightning across cosmic night. They are the universe's punctuation marks, brief, brilliant commas in an endless sentence. They remind us that even in a cosmos governed by gravity and thermodynamics, there are still surprises. Somewhere, perhaps at the edge of a galaxy or between galaxies entirely, matter stumbles into something new. A star collapses the wrong way, or a black hole tears at its edges, and for a few hours creation and destruction overlap in a single burst of light. That's what science looks like when it dreams. Tiny anomalies that rewrite the rules. Then there's dark energy, the quiet backdrop behind every star. It's the slow, invisible force that makes the universe larger with every breath. It's strange to think that the thing holding everything together is the same thing pulling everything apart. We still don't know what it is. Vacuum energy, a cosmic constant, or perhaps the whisper of other universes pressing against ours. But maybe it doesn't matter that we don't know. The act of wondering might be its own kind of gravity, keeping our minds orbiting around mystery rather than drifting into certainty. On the smallest scale, the photons remind us that reality isn't solid, it's participatory. Every time we look, measure, or think, we collapse one version of the story into being. Light travels for billions of years, uncertain of what it is, until it meets an observer. Then, in that instant, it decides. Wave, particle, both, neither. Observation doesn't break the laws of physics, it completes them. You could almost call it compassion, the universe waiting for someone to notice before finishing its sentence. And then, on the vastest scales, we find the rogue planets, pairs of wanderers bound only to each other, holding fast in an otherwise empty sky. They're proof that not every system needs a centre, not every orbit needs a sun. Sometimes, connection itself is enough. Even the cosmos practices companionship, quietly demonstrating that structure can emerge from loneliness. And somewhere far beyond them, in that quiet corner of the galaxy, the radio beacon keeps ticking. A neutron star spinning more slowly than any we've seen, breaking the rulebook by staying bright long after it should have gone silent. We still don't know why it persists. Maybe it's a magnetar in disguise, maybe something entirely new. But its message, steady as a metronome, reminds us that endurance can be a kind of revelation. When you line up all these enigmas side by side, something remarkable happens. They stop looking like separate problems and start to feel like chapters in the same story. Each one reveals the same underlying truth, that nature doesn't resist understanding out of cruelty. It does so out of depth. The world isn't trying to hide. It's simply too vast to fit neatly into one human mind. Scientists sometimes describe these mysteries with the word anomaly, as if they're errors in the data. But anomalies are where progress begins. Every leap in knowledge, relativity, quantum theory, DNA, evolution, started with something that didn't fit. The flicker of starlight that refused to behave, the experiment that gave the wrong number, the shadow in a photograph that wasn't supposed to be there. Discovery begins not with certainty, but with a raised eyebrow. And perhaps that's why science feels so human. We too are full of contradictions, beings of logic and emotion, of reason and intuition. We are both observer and participant, shaped by the very things we try to understand. The more we study the cosmos, the more it seems to mirror us. Vast, unpredictable, and filled with potential we haven't yet measured. There's an image that often comes to mind when astronomers talk about these mysteries. They describe the universe as a great fabric, stretched and curved by matter and energy. Galaxies rest like knots in its weave, light glides along its threads. But maybe the fabric isn't just physical. Maybe it's also a fabric of questions. Each discovery is a tug on one thread, rippling through the rest, changing the entire pattern. We never really see the whole thing. We only feel it tightening under our curiosity. What holds all of this together, from blue flashes to quantum choices to impossible pulses, is not knowledge, but humility. To wonder is to admit that we don't know, and to keep wondering is to fall in love with not knowing. It's easy to mistake confusion for failure, but in truth, confusion is the beginning of clarity. A scientist once said, "The greatest gift of science is to remind us that we are small, but capable of large questions." Maybe that's why so many of the universe's riddles sound poetic when spoken aloud. They're not obstacles to progress, they're invitations to listen more carefully. Every flicker, every pulse, every whisper of radiation is the cosmos saying, "There's more. Keep looking." And so, we do. We build telescopes on mountaintops and satellites beyond the atmosphere. We fire lasers into the dark and catch their echoes years later. We study the faintest ripples in space-time and the smallest tremors of particles, not to conquer mystery but to befriend it. In doing so, we weave our own thread into the great cosmic fabric, one made of curiosity, patience, and wonder. Maybe that's what connects all these phenomena, from the impossible star to the flickering blue light. They are not just problems to solve, they're reflections of our need to keep asking. Each one humbles us, and at the same time makes us a little more infinite. In the end, perhaps nature isn't trying to trick us at all. Perhaps it's teaching us how to listen, not for answers, but for patterns. Each unanswered question is a melody waiting to resolve, a whisper in the silence saying that mystery itself is the purest form of knowledge. There's a special quiet that settles in when a night of observation ends. The telescopes are parked and covered, the last data files are saved, and the control rooms hum only with the soft rhythm of cooling machines. Outside, the stars remain, unbothered, unchanged, still singing their slow light toward us across the dark. It's in that hush that scientists, after years of chasing answers, often find themselves face to face with something more profound than any discovery: the comfort of not knowing. Tonight, we've wandered through questions that have no neat conclusions. We've seen stars explode in ways we can't yet model, invisible forces stretching the universe apart, particles acting as though they remember the future, and orphaned planets that make homes in each other's gravity. We've heard the steady tick of a dead star's heart and watched time itself behave like water, rippling both forward and back. None of these mysteries are solved. Some might never be, and yet, that's precisely what makes them beautiful. Humanity has always tried to map the unknown, to name constellations, to draw borders around chaos, to turn questions into equations. We measure, we calculate, we model, as if the universe were a riddle waiting for us to fill in the blanks. But the more we learn, the more the blank spaces multiply. Knowledge doesn't erase mystery, it deepens it. Every door we open reveals another hallway. Every solved equation leaves behind a faint echo, whispering, yes, but why? And maybe that's the point. Maybe the goal of science was never to reach an ending, but to fall endlessly into wonder, to trace the outlines of reality with fingertips that never quite touch the edge. Because what's out there, those flashes of light, those trembling frequencies, those impossible clocks, isn't just information. It's an invitation. The universe doesn't hand us certainty, it offers conversation. When you listen to a scientist describe their work, even the most technical among them eventually speaks like a poet. They talk about listening to the cosmos, about light echoing through time, about the memory of stars. Beneath the calculations, there's something tender, a recognition that we are part of the mystery we study. We're not standing outside the universe looking in. We're threads in its fabric, trying to see the pattern from within the weave. Think of all the ways we've tried to see farther, to catch starlight, to measure the faint pulse of gravity, to send machines to the edge of the Solar System. The Voyager probes, still drifting through interstellar space, carry a golden record etched with the sounds of Earth: wind, water, bird song, laughter. They were launched in the 1970s, but their journey continues billions of kilometers away. One day, perhaps long after humanity itself has changed beyond recognition, those records might still be playing somewhere in the dark, a faint reminder that we once looked outward and wondered. That impulse, to send a message into the void, is the same one that drives every experiment, every observation, every late night in a laboratory. We are by nature curious. We can't help it. We look up because the stars are there, and we ask questions because silence is too vast to bear without dialogue. And when the universe answers, even in whispers, it becomes a little more human, and we become a little more cosmic. Some nights, astronomers speak of their work as tending a lighthouse. The light they keep isn't for ships, but for understanding itself. They polish mirrors, calibrate instruments, write lines of code that sift through oceans of data. Most of what they find doesn't make headlines. It's background noise, calibration errors, subtle traces of something half seen. But occasionally the data flickers in just the right way, and the impossible becomes visible. A pulse where there should be none, a flash that rewrites the laws, a pattern that hums softly between order and chaos. Those are the moments when science becomes almost spiritual, not because it gives answers, but because it makes us feel the immensity of what we don't yet know. It's easy to forget that mystery is not the opposite of understanding, it's the foundation of it. Without the unknown, curiosity would have nowhere to go. Wonder is the raw material from which all discovery is made. To live in a universe with unanswered questions isn't to be lost, it's to be alive. The not knowing is what keeps us reaching, keeps us learning, keeps us human. In a way, we're all explorers of the same kind, the kind who navigate by questions rather than by stars. We move through our lives like astronomers in miniature, charting patterns in our own experiences, trying to find meaning in the dim light of what we can perceive. And sometimes, in the quiet moments between answers, we catch a glimpse of something greater, that we are participants in an unfinished story, each of us a small note in the music of existence. Perhaps the universe, in all its complexity, doesn't need us to solve it. Perhaps it simply wants to be noticed. Every experiment, every observation, every act of curiosity is a form of noticing, a way of saying, I see you. And in return, the cosmos answers in its own language, through pulsars and photons, through gravity and time, through questions that echo rather than conclude. So tonight, as we drift toward the end of this journey, let's not think of it as an ending at all. Let's think of it as a pause, a breath between questions. The mysteries we've explored are still out there, unfolding in silence. Somewhere, another LF bot is already flaring. Another beam of light is interfering with itself across time. Another rogue planet is circling its twin in the dark, and another radio pulse is leaving a dead star, beginning its long journey toward us. And maybe, one night far in the future, long after our own voices have faded, someone else will listen and hear that same steady rhythm, the heartbeat of the unknown, and feel the same quiet awe. So wherever you are right now, beneath city lights or in the still countryside, under clouds or open stars, take a moment to listen, to the hum of the world, to the small ticking of your own heart, to the shared rhythm that ties you to everything that ever was and ever will be. Because that's what science really is, not the pursuit of certainty, but the celebration of curiosity. And so, we've reached the end of tonight's exploration. Whether your eyes are still open or you're already drifting between waking and dreaming, thank you for wandering through these mysteries with me. If you'd like to join again for more quiet journeys, you're always welcome here. The universe will still be waiting, full of questions that glow softly in the dark. Sleep peacefully wherever and whenever you may be.